let's jump into it. Welcome everyone. You're at review session 4. Post reading week. Hopefully everyone's doing all right. As usual, we're your hosts. I'm Robert, and I'm with my co-host here, Steven.
How's it going, everyone? Hope you guys are all having a good week after reading week, getting back to school. Hope everybody had a relaxful reading week, and let's jump right back into some CP164 review.
Right on. So we're gonna be going over linked lists, link priority queues, and recursion today. So some pretty big topics. Linked is super important, and recursion is super important. So definitely stay tuned throughout the session today. So go to the next slide here. As usual, you guys know, just sign in. You can scan the QR code there, or you could type in that link. If anyone's in chat from LCS, can y'all post the link in chat so it's easier? Actually, here I could probably handle that real quick. There. That link should bring you to, let me just make sure I typed that correctly. Yeah, to sign in, you could open that up on another tab, and I believe this goes towards the Laurier experience record. If you attend, I think, 2 or 3 of these sessions, you get to have that on your experience record, so good stuff. All right. I think I can move on to the next slide. It's on. So, we're almost at the end of our sessions, unfortunately, and we're currently sitting at 4 out of 5. So, yeah, the last one's really just a final review session, which hopefully gets a good turnout. And yeah, so you guys are almost done CP164. It's awesome. Good stuff. And so today's agenda, what we're going to be going over is link structures, linked lists, link priority queues, and recursion. Just like I mentioned earlier, some pretty big topics today. And as usual, we have our links, some useful links. So we have the math and stats learning support. Would recommend if you guys are struggling in any of the math or CS courses. Those links are there. You could also find those in probably most of your syllabuses. And some coding sandboxes, which we highly recommend if you guys want to code something on the fly or follow along with us during our sessions. We got REPLIT and CodePen here. And the cheat sheet, this link here, this is like a quick little link on link lists and whatnot from Code Academy. You could even find this if you type link list cheat sheet like Python into Google. You'll find this is from Code Academy. It's pretty good. I just found it before the session today, so I decided to add that in last minute.
All right, so I guess we're just going to hop right into linked structures. We're going to talk about what they are and their basics and some common use cases and how we can traverse them and how they differ from array-based structures that we learned beforehand in CP164. So what are linked structures at their core? Linked data structures are built with multiple nodes where each is connected using pointers to the next node in the structure. So for instance, if we have a linked list, each value is made up of a node instead of an integer or a float or a string. And this node has a value attribute and a next attribute for the linked list. We'll cover a few more linked structures later on that have more than just a next. So a doubly linked list, for example, that has a next and a previous attribute, and a binary search tree, which I'm pretty sure will be covered in CP164, closer to the end, closer to the final exam, which has a left and a right node. And yeah, so for example, the node in a linked list has a value attribute that holds the value itself, and a next attribute that holds a pointer to the next node in the linked list. So some common use cases, like we mentioned, are linked list, linked queues, binary search trees, And one of the most trendy ones
Yeah.
in the past few years has been blockchains.
Yeah.
So if you guys know how blockchains work whatsoever, it's pretty much a simple linked list where each transaction and like block of data is connected to the other through chains. And that's why it's really called the blockchain. And in essence, it is just a linked
Linked
data
list.
structure.
Yeah.
Yeah.
Right on.
So we just have like a small example just to simplify linked structures a little bit, because I know it can get a little bit tough to wrap your head around just because we're so used to array-based structures. So let's just think about a train route. So each of these squares or boxes, should I say, are train stations, and the train can only move in one direction. So um, each box has a value, and that value is the city it's located in, and a next attribute as well, which is the only other train station it can go to. And so each box represents the value itself, and each train track between the boxes represents the pointer or the link to each of the other nodes or train stations in the whole structure itself. So they really rely on each other, these linked structures, to like have data that we can traverse and that we can use in a way that's like simple to understand and similar to the array based. So yeah, Robert's going to talk a bit about linked lists now, get more into the specifics of these linked data structures.
Yeah, so let's jump into linked lists. Small hint is we were kind of just looking at one right there. So let's jump into what they are in a little more detail. So here's a little bit of a diagram here. We have our head, and the head of a linked list. I'm just gonna pause this. The head of a linked list is the only like really unique node, as it's the only node in your list that well, actually, sorry, I'm thinking of a blockchain, which is different. The the only unique one is the end of the list, which does not have a next. It's set to null. Um, the head is the start or the first node that was added to the list. So every time you add to a linked list, you simply just edit the next you need to edit the next attribute of the current last node to whatever the new node is that you're essentially appending to the end. So this way every node has a value and a next value, and the last node's next value will always be set to null. This way, when you get to the end of your list, you'll know you're at the end because the next will not be defined. It'll just be null. It's like I'm at the end of the tracks here. Like there's no station to go to. So let's just move into a little REPLIT example. You want to pull that up, Steven?
1 second, let me just share my screen so
Yeah,
you
no
all can
worries.
see it. Yep. Okay. Rob, let me know if it's all good.
Just give me a second. Need to pull it up on Discord real quick. All right, that should be good.
All right. So all of these functions should seem pretty familiar to all of you guys, just from the array-based list itself. But this class right here is going to have to be added additionally because just because the node itself needs a data structure because it is more complex than just a value. So we initialize this node with a value and a next value, and those are just put into those attributes. And we identify this list with this constructor where the front is none, the rear is none, and the count so far is 0. So we just have an empty list. And we can check if this list is empty by asking if front is none, or on the other hand, we could also check if count is 0. It'll really do the same thing. But like Robert said before, lists are, you can only like add, in a linked list, you can only add to the end of something just because of how they're linked. Each node must be linked to another one. So you can't just like,
Break the
I'm
chain.
sorry.
Break the chain.
Yeah,
Like
yeah, you
yeah,
can't break the chain. Sorry. I couldn't find the right words. My
yeah.
bad.
It's all good.
So now we have this private length function where we just return the count. And so these append and peek functions are going to look very different from the array, just because the traversal of these linked lists really depends on the links themselves. So yeah, so here we create a new node, and this is just going to be the node that we're appending to the list. Just because we can't append the value itself, we have to create a new node with the value inside of it. So here we check if the list is empty. We add the node to the front of the list, and if it's not empty, we say we take, since we're adding to the very end, we take the rear of the list and make its next value the new node. And so regardless of if the list is empty or not, we always set rear to node, just because we know that we're appending to the very end. So the new pointer for self rear is going to be the node itself, and we're adding count. We're adding to count just because we know we're adding. And this peek function is just a little bit different too, just because we have to traverse to find which value we actually want. So if I is less than 0, this is just saying, just because when you're indexing a list, you can't have a negative value. So we want to have the same sort of functionality when we're working with linked lists. So here we're just adjusting the I value so that it's still able to be worked with in this while loop here. So then we say while j is less than I, so we're just going through the list. So current is equal to current next. And so that just means we're starting at current is the front. And so peak, we want to find the index at I. So we want to keep going in this while loop until j is equal to I. So we keep going, current goes to current next, and we just keep going. So it's the same thing as traversing through an array-based list, but we just have to use the links that we have. So it just gets updated to the next and updated to the next until we find the value that we want, and then we deep copy that value and it's returned. And this return value, it's not really important, it's just for testing, and we're just taking every item in the list, every node, and printing out its value. Or well, we're not actually printing it out, we're just giving it to a list, and that list is being returned. So this example is going to look pretty familiar to those of you who attended the midterm review. It's pretty much the same thing, the diary example, except we're using a linked list, so it's just going to be a little bit different. Yeah, so let's run through that really quick. So we have the init function, we're just making it this list, so this linked list. New entry is just going to be appending to the end. View entry, we can give it a day that we want to see, and it'll give us that value, and return entries is just the return values, that's right here. And so if we run this example really quickly, so you can see that these are the entries in just a normal list, and we want to add them to the linked list. So this is after the first one is added. We can go to the next one, the next one, and the next one. And so now, if we want to look at an entry, I can type in 1, for instance. So it should give me the second one, just because we know that list's indexing starts at 0. And so it'll give me the second one, and that's indeed the second one. And now it's asking me if I want to add a new diary entry. So let's just say new entry. And we can see now that at the end of the linked list, we have new entry. So yeah, that's pretty much just how linked lists works, and a little bit about the traversal and how these functions are implemented differently than the array-based list. So I'll pass it back off to Robert, who's gonna start explaining the linked priority queue. Just because the queue is very similar to the list, it's implemented very similarly. It's just, you guys know how queues are implemented. You just have to use the traversal techniques that are shown to implement those ones, but priority queues are just a little bit differently, and Rob's going to explain why.
Yeah. Alrighty. So let's jump into maybe what a linked priority queue is. So you guys are already familiar with priority queues and how they work on the conceptual side of things, where you have a priority value, and that value, the lower it is, the higher priority that whatever it is may be. It'll be closer to the front of the queue than something with a higher value, which would be closer to the rear of the queue. So an important thing to note is that each node has a value and a next value, just like your linked list that we just covered and our link structures. And the nodes are sorted based on their priority, as I just mentioned. That's the only real addition that we're making. And to compare this to a standard queue, so let's say like a standard linked queue, and comparing that to the linked priority queue. A priority queue is more difficult and less efficient to insert a node, where a queue you would just insert the node at the end, right? You just append it, you would update your next value to the new node, and then you would have a new node at the end of the queue. Well, a priority queue is different because now we have an extra variable that we need to deal with and organize the queue such that these are in the right order, because as soon as we lose that order, the priority queue is useless. So that's why it's a little bit more difficult. And to make that happen, we actually need to iterate through the entire priority queue to find the spot that this new node fits. So that would be your O to the n time if you were looking at the time complexity of this. We need to look through each node in order to see where this one will fit in. And that's really the main difference between the two, the priority queue and the standard queue in a linked structure specifically. So yeah, we have another REPLIT on this
All right,
one.
yeah, let's hop into this example. So priority queue is set up very similarly to the list with its constructor functions. So these are very similar. We don't really have to cover those. But as you guys can see, the insert and remove functions are very different just because we do have to iterate through the list, like Robert said. So we want to have 2 pointers, a previous, which is set to none for now because it's just going to be looking at the value before current, and current is just going to be set to self front. So while current is not none, so while we're not at the end of the list, and while the value that we have is less than the current value, previous equals current, and current equals next. So now we're just traversing through the list, and we have 2 pointers now. So just think of it like this one's just outside of the queue right now, and this one's on the first value, and it just shifts over like this every time until we find a value that is either greater than, or just greater than the current value. So now we create the node, and we're just going to be inserting it very similarly now to how we were inserting it before, except it's not going to be at the end, so we need a few more tweaks. So here, if we say, this is just saying if the list is empty, we set it as both the front and the rear. If previous is none, so if you want to insert at the first value, you just say self front is node. If previous is the last value, so previous is here and current is outside, you want to insert at the very end, you say the same thing as how we were appending. So you say rear next and rear are both node. And in the else case, we say previous next is node. So we take the previous of the current and we put it right there. And then we just append the count +1 just because we're adding a node and we know that. So the remove function also a little bit different. Well, we didn't really look at a remove function for the list, but it's similar to the peak function a little bit. So this one is actually, wait, the remove function, sorry. It's just going to be looking for the highest one. So it's kind of like the peak function, but in the sense if you were always looking for the highest value. So we just want to make sure that, so we're asserting that the count is greater than 0 because we can't remove anything from an empty queue or list or priority queue or whatever, any structure. So we say the value is, the front value, and then we say front is next because, since we know from the insert function that the highest priority will always be at the top of the queue, we know we just have to take the first of the queue. So here we're just taking the first and setting the first of the queue now to the next of the first. So we're taking this one, we're taking it out, and we're moving this to the front. And so we just have the correct pointers. And we're decrementing the count just because we know we're taking. And here we're checking if self front is none, self rear is also going to be none. So if we took out the only node from the linked queue, the rear will also be none just because there's no more nodes, and we know that any linked structure will have its front and its rear. Well, ones that have front and rear, both of them will be none when they're empty. So a linked queue can really be described as, let's say, a hospital line. So patients come in with different severities of illnesses, and we want to tend to those that are more severe than others, for example. So let's say somebody has a concussion, we probably would want to deal with them before somebody that just has like a jammed finger or something. So a priority queue would be really efficient in organizing these right away just from insertion and just removing or checking in the most severe patient right away. So here, the hospital is constructed using just a priority queue. The check-in is just an insert. The call patient is a remove, and show patients is very similar to what we were doing with the list. It's just for testing purposes. So let's say we have 3 patients waiting to be checked in. Their severities are 3, 5, and 2. So we create the hospital, and we're checking in the patients. So the first patient comes in line. He's obviously going to be the first one just because there's no other patients in the line. Now a patient with severity 5 comes in. So they're going to be placed on top, as we can see here. So it goes 5, 3. And the 2 should be placed at the very bottom. So let's say now a new patient walks in with the severity of 6. So now they're going to be placed at the very top. And now let's see what happens when we call a patient. We call a patient, and the 6 gets removed from the priority queue. And we can just keep calling patients, and the 5 is going to get removed, the 3 is going to get removed, and the 2 is going to get removed just by priority. So yeah, that's pretty much how a linked priority queue is implemented, a little bit of functionality. So I'll go back to Robert, and he'll just start off with the explanation of recursion, and we'll look at some more examples and REPLIT examples.
Yeah, so let's jump into some recursion now. This is probably our most difficult topic for today is recursion, and probably the one that you guys will probably run into the most problem with kind of wrapping your head around if you haven't figured it out already or are still having trouble. So let's start off by defining what recursion is. So recursive functions are functions that call upon themselves. So recursive algorithms have 2 main parts, really. You have a base case, and this is where the recursive call ends and it actually exits out of itself, where it stops calling on itself. It's the last thing to run, and it's where it exits. And the recursive cases. So these could be one or many recursive cases, and this is where the function is called and passed a different or modified parameter value than what was previously passed to it. So let's say like I passed in like 5 to my recursive function, and I had like a base case of like 1 or something like that, and then I had my recursive cases that would take 5 and like -1 each time. So I'm changing the parameter every time that I repass it into itself. So I'm doing a different operation. This way, your goal should always be to reach your base case, because if you never reach your base case, then your recursive function never ends, and you'll, just like an infinite loop, you'll infinitely be adding to your memory in the stack. So let's look at a common use case. So a common one, if you guys haven't seen it already, is the Fibonacci sequence, the Fibonacci numbers. So when I was referring to something like a base case, this is what it looks like here for Fibonacci. So we know that our end needs to end up at the very end being 1 or 2, and then we return a result of 1. And for every other case, we know that we need to run what would be like a tree for this recursive call. So you have different kinds of recursive calls. You can have linear recursion, which is where in every call, like you only call the recursive function once. So let's say I run this Fibonacci sequence and I have a number in as n, and if this wasn't binary, as in like calling it 2 times for every 1 time, it would be just a single one, and then that would create a linear recursion. So this is binary. So for every time Fibonacci is called once, it splits off into 2 different sections, or 2 different recursions after that. So this is getting kind of complicated. I'm already almost getting confused myself, but the way you got to think about it is that every time you call the function a recursive function. So you call a function inside of itself, it adds itself to like a stack, and the stack is your memory. And you have to understand that every time you are calling the function, it's not running the function really in the way that you think it is. It's not running in like the way it would run if you were calling it from like a main function. It's not in that order. It's actually like a bottom up order. That's why our base case is 1 here. So if you think about it, if this was running in like a non-recursive way, we would just always end up like returning 1. But that's not really what's happening here. What's happening here is that we're running these recursive calls which get added. So let's say my Fibonacci, if I do like n is equal to like 5, 5 will come into this function. It'll check, is 5 equal to 1 or is 5 equal to 2? Well, no, it's not. So let's skip this. It's not our base case. So we run it through the recursive case, and we take 5 minus 1, and we take 5 minus 2, and we repass that into our function without returning anything. That's the key. The key is that we haven't returned anything yet. So now we have a split. If you imagine, if you write this on paper, we have, if you had Fibonacci of 5, you would draw like 2 like branches coming off of the Fibonacci, the first call, and you would now have Fibonacci 4 and Fibonacci 3. I'm trying to like do it with my mouse. You'd have like 2 branches like this coming off of this with each one of these. And then that'll happen again until we're passing in 1 or 2. So one of our calls from 5 would be 2, and we would reach a base case, and a result would be 1. And then the other one would go through again, and then that would give us our final recursive call, and then it would work itself up like backwards through that to finally give us our answer. I'm not if anyone has any questions, throw them in the chat. Recursion's like super confusing, so like don't worry about it. I might be like talking in circles, I don't even know.
I mean, recursion is kind of a circle. So
Yeah. You really have to do it to understand it. Like you have
yeah,
to do a lot
exactly.
of it.
Mhm.
So just
We're
practice,
gonna
practice, practice.
we're gonna go over a couple recursion examples just to, I don't know, really try to familiarize ourselves with it just a bit more. So here's this phone call example I kind of like to pull out sometimes, just because, I don't know, it's kind of relatable, especially in university when you have a group of friends, but like you're not really friends with all the people. You're only friends with like 1, maybe 2
Right.
people. Let's say 1 in this case. So here we have a list of friends: Obi, Safe, and Robert. And Obi decides he wants to go have lunch with Safe and Robert, but Robert has the busiest schedule out of everybody. And Robert usually decides when they all have plans. Obi does not have Robert's phone number. He only has Safe's phone number, and Safe has Robert's phone number. So in this case, Obi calls Safe, and if you see here, the function is called phone call. So we're just assuming that whenever this function is called, it's just going to be a phone call between the first person and the second person in the list. So since it's not, the list isn't empty, we haven't hit our base case yet. So we go to our else. So here, lunchtime equals phone call of list indexed at the values after 1. So this pretty much just means that we're taking just the first value off. So Obi is no longer part of the equation. It's just between Safe and Rob now. So Obi's called Safe. He's told him he wants lunch plans, but he doesn't know when to do it, and asks Safe if he can call Rob. So Safe, it runs through the function again. He does a phone call, and since we're not at our base case yet, it goes again to the recursive call. And so lunchtime equals phone call of just a list of Robert now. And so Robert, like this list empty really should be just like one list has a length of 1, but it doesn't really matter. It's the same principle. So lunchtime, now Robert has nobody to call, so the phone call just like calls again, and Robert knows that the lunchtime is 1 p.m. So now if we think about it, Robert has to relay this information backwards. And since these function calls have not yet been returned because we haven't hit this return, he can relay that information back using this phone call. So we know that lunchtime equals 1. So this lunchtime will equal phone call. So phone call of the list of 1. Sorry. Phone call of the empty list will equal 1. And so now we know that lunchtime for phone call of list indexed at 1 and everything after for the list with just one element will also have a value of 1, and so on for the list with 2, and so on for the list with 3 people. So now Obi has the information that Robert wants to have lunch at 1. So I know that's like a little bit of a confusing example, but I promise you guys that with this REPLIT example, we'll understand it just a little bit more because we're going to see how the functions are actually called, and you'll understand what this like relaying of information really means and what this this top-down stuff that me and Robert keep talking about is. And just visually, it's going to be a lot more visually appealing, and you're really going to understand what's going on. Okay, so another very popular function, like mathematical function or just calculation that uses recursion, is the factorial. So factorial, I'm sure all of you guys are familiar, but if somebody in here isn't familiar, factorial is, so let's say we want the factorial of 3. To get the factorial of 3, we have to multiply 1 times 2 times 3. So all the numbers starting from 1 going up to 3. So this is pretty evident in our Python implementation of it. So our base case is going to be 1, just because we know that the factorial of 1 is always going to be 1, or n in this case. So we get 1, and we return 1 if this were ever to be passed here. And then our recursive case is just going to be 1 times factorial, or n, sorry, not 1, n times the factorial call of n minus 1. So let's say we want the factorial of 2. This would run through here. It would be 2 times factorial of 2 minus 1, or factorial of 1. So then we have this 2 stored, and we want to figure out what factorial of 1 is. So then we run it back, and we know that n is equal to 1 here. So we return 1. So now we have 2 times 1 is what our function is going to equal. So we return 2. So the factorial of 2 uneventfully is going to be 2. So let's run this function we're going to be calculating the factorial of 5. And we're just going to be seeing how all of these functions are called and how they expand and then they contract back into one answer. So we start off with the factorial of 5. This obviously doesn't meet our base case. So we're going to go to the else, which is going to be n times factorial of n minus 1. So this is going to be the factorial of the factorial of 4, just because we're calling factorial again on 4, correct? We're going to keep going, 3, we're going to keep going, 2, we're just going to keep going. So recursion works in a way that you keep calling functions on top of each other. Most cases, it really varies for different cases, but for this case, you're just going to be calling functions on top of each other until you hit your base case. So it's very similar to a loop in that sense, where when you get to like the loop's argument, let's say, it stops and it like returns a value. So we keep going, and when we get to the base case, which is 1, we know we have to multiply 1 times factorial of 0, which we don't have. Oh, sorry, no. When we get to 1, we know we just returned 1. So here, this factorial 1 is just going to be 1 times 1. And then we keep going. So this is going to be 1. So obviously we're going to be passing factorial 1. And the n now is going to be 2. So we're doing the previous times the new n. So 1 times 2, and that's going to be the factorial that we're calculating. So now we have 2 as our factorial call, and now we have 3 that we're going to be multiplying into it. And then 3, the 2 times 3 gets carried down to the 6 here, and then the n again is going to be the 4. And so now we have factorial of 24, and 24 times 5, because that's our last n, because we're going factorial of 5 is going to be 24 times 5, and then the factorial of 5 is going to result in 120. So as you guys can see here, the functions expand out. So this is all the function calls here. And then when we have the big return function, it compresses down. So it's very much like, if you think about it, coming down like the memory stack, how Rob was saying, it comes down and then it all gets calculated back up. So that's the main concept of recursion, is that you want to keep performing these tasks until the base case, but the tasks aren't calculated yet until we hit the base case. And then it just gets compressed down all the way and we have a final result. So if we can see here, it's very much like a normal distribution. And in that sense, recursion is very beautiful just because it's very symmetric most of the time, especially with like binary recursion, how we were talking about before. It like spreads out into a really nice tree and then it all comes back up. It's really nice. And you guys like just have to keep practicing with it and you're really going to get the hang of it. Like, I'm sure it really all comes down to practice. Like, I know when I was in CP164, I was super confused just because recursion is a pretty hard topic. And yeah, so just like keep practicing with it, and I'm sure you guys will get it.
I just made a little SketchUp thing here that kind of visualizes it. Maybe I could share my screen to you so you could see what I'm looking at too. I have to make this visible to the stream. Oh, here. Oh, I could do it this way. Okay, perfect. So I just need to do like this. I just need to add these arrows real quick. This is kind of like the visualization of like what you were just saying, essentially.
And you guys can see just from this example, I know the next thing you guys are going to be learning in class is kind of like recursion with linked structures. And just because of like what we're doing here, you guys can kind of see why recursion is so important with linked structures, and especially with binary trees, as you'll learn later on, why you're going to need to use recursion and why it's so important for these types of structures. Just because like if you see, all the function calls are linked together, and like the similarities will really like transfer over to when you're traversing through the lists.
Yeah, so I just made this quickly just to reinforce what Stephen was saying. So like the key to know is like we don't actually return anything until we hit our base case. So like the key to thinking in a recursive like mindset is really thinking like bottom up. Because that's what ends up happening. Like you reach your base case and then you work yourself back up through your returns to get back to your original function call at the top. So yeah, if this diagram helps, I'll leave this on the screen. Maybe I'll screenshot it and put it somewhere. I don't know. But yeah, that's all I wanted to show real quick. I'll transition us back into the slides. Stop sharing my screen. Oh, do we have a REPLIT example?
Yeah, we already went through it.
Oh, we went right.
Yeah.
I'm behind on the slides then.
No, it's all good.
All right, yeah. So that brings us to the end actually. So perfect. If anyone has any questions, drop them in the chat. If you want to see
Yeah,
the recursive diagram again, I could bring it back, or I could even show the binary one for the Fibonacci numbers.
For sure. Let us know if there's anything that you guys want us to go over again. We're gonna be here for a little bit longer. If you guys just want to ask any questions, feel free. Yeah.
And like usual, fill out the feedback. We do read it and we do listen to you guys' feedback. We're always trying to improve these all the time, week after week. So if you guys see anything we need to improve, more examples, maybe different maybe format of how we do these, maybe less lecture like, if you want us to do it more Q&A and take questions from you guys more, whatever it may be, leave us some feedback. We'll look at it and incorporate it. I'll give you guys a second to open up this link here. And if anyone from events is in chat, which I don't think they are, but Yeah. And then I don't believe we have another slide after this one. Let me just, no, this is our last one. So I'll kind of just leave it sitting on here if anyone has any questions. We'll probably stick around, I don't know, depending on how many questions get asked or something, maybe another like 10 minutes, 5-10 minutes. Actually, I might make the same diagram for the Fibonacci one.
Yeah, it'll be helpful as well. Just because I know last review session I was trying to explain it with my hands and it was
Yeah.
working
Did
out.
not work out well.
Yeah.
Trying to do hand signals. Okay, Fibonacci, yeah. Just do that on the side here. I think still no questions in chat, unfortunately. Oops. Let's see, 4 minus 2. Maybe we should fill the air. I don't know. What do you want
Yeah,
to
let's
talk
come up with
about?
some quips, some banter,
Yeah.
or or our two loyal viewers at the moment
Yeah.
stuck
Oh, no,
around.
no, we got 5 on my end here, but I
Oh,
think one of
really?
one of
Okay.
them's me, so
One of them's also me.
yeah.
So
Just bear with me as I make this example. Oh shit. That goes there.
hopefully the turnout for the finals just as good as the one for the midterm.
Yeah. Here, let me just I'm gonna share my screen. Just so and I'll change this to the pop out like this. Boom.
Nice.
I was just doing the arrows. I'm not complete yet, but just gotta do like the tree here. And then this is really here, let me change this. I'm gonna go like this.
Nice.
I made it worse.
Looks like Batman.
That's facts. All right, yeah. So this is like what we were talking about earlier with it being a tree in comparison to something that's linear. I'm not gonna do like what the return looks like, because that's like kind of a nightmare. But if you understand how this works, it works exactly the same here. So we know that for Fibonacci, is the base case return, is it just one? Is that right?
Uh, yeah, the base case return is just one.
Is
So like
one.
just because the first two like elements or numbers of Fibonacci are like 1 1 and then it adds on
Right.
afterwards. Yeah.
Okay, yeah. So for every time we reach one of our base cases here, it begins to work itself back up the tree, uh, with starting at returning 1. So like this will return 1, this will return 1, this will return 1, and this will return 1. And like where is it returning 1 to? Well, it's just returning 1 to the last function that called it. So it's going back up a step, and now we have 2, and then I believe from here I need to look at the code again.
Yeah,
But
you just add them. So
you
like
add them.
this
Okay, so
becomes 2, and then the 4 minus 2 is also a base case. So it's going to be 2, the 4 minus 1, and then 1 at the 4 minus 2. And then it just adds to 3 for the 5 minus 1. You know?
okay, yeah.
Yeah. And then, yeah, the 5 minus 2 is 2. So then you add the 3 and the 2, and then the Fibonacci of 5 is 5.
Wait, so that again?
So the 5 minus 2, like the
Yeah,
right side one, is going to be equal to 2 because you're
right,
adding the 1 and the 1, right? And then you add the 3 and the 2 to get the 5 at the top. Just because the
right.
actual Fibonacci of 5 is 5.
Oh, okay, that's why I was.
Yeah. Yeah.
Okay, sweet. Yeah, so that is this right?
Yeah,
Wait,
that's it.
yeah, okay.
The 4 and
So
the 1 is 2, and then the 4 minus 2 is also a base case. Just because,
right,
yeah, it's
I
1 as
see, I
well.
see.
Yeah.
Okay, yeah, I was tripping over that a little bit. Just shows how hard recursion is.
Yeah.
So yeah, some examples in case everyone had trouble visualizing it. I kind of want to delete this. It like does not look good.
Yeah, you can just say base case, like hit. So the base case is just hit whenever the return result is 1, for instance.
Right. I believe it's 1 or 2, right, for base case.
Oh,
So
I'm just saying, like the return,
yeah,
the return.
yeah, exactly.
So, yeah. So if you guys just want to
It's 1 every
know
time
when
for
the base case
Fibonacci.
is going to be hit, yeah.
Right. Yeah. That's about it. I don't think we're not getting any questions in chat or anything. So
Yeah, I
I
guess we'll
think
give one final ask. If anybody has any questions, just feel free to drop them in the chat. We'll answer them. If you guys want us to go over anything that maybe you didn't really understand throughout the review session, we can just look over that again. And if not, it
I'll
was
give
good
it
having you
another,
guys.
yeah, I'll give it another
Yeah,
10 seconds. If someone hasn't typed something by now, I don't think anyone's gonna. And
yeah.
I could see all our viewers are gone too, so
All right.
it's just us. But yeah, all right. It's a good session as always. If you guys have any questions, reach out. And we'll catch you for the final, which hopefully we get a much better turnout than this session. Because yeah, it'll be good. We'll try our best. And again, use this feedback if you want the final review session to be the best it can be. Fill this in. So sweet. All right.
Yep.
Take care, guys. Great session. Awesome.